Sup guys? So today we're going to be doing some dynamics, more so fluid dynamics, with the emphasis on terminal velocity. Now I'm going to give you a quick introduction of how terminal velocity works. So terminal velocity, it's not a particularly difficult concept. Like it's not as difficult as something like momentum, even I'd say projectile motion, but the key is knowing how the graphs work, especially in paper 1. And I'm specifically referring to the VT graph and the AT graph. So I'm going to explain how terminal velocity works first from, I'd say, just intuitively what's going on. So let's say there's a person and he's about to jump. At this moment, he has 0 meters per second. But then as he's falling down, his velocity is going up. So he's increasingly falling down until he comes to one point where he just maintains that speed. So he's still falling down, but he maintains that speed so that v remains constant. And the reason for that is at this moment, so when the velocity is increasing, uh, the acceleration is effectively non-zero, but the increase in the velocity or the change in velocity is effectively decreasing in the sense that the rate at which you're increasing is slowing down, slowing down, slowing down until the point where the rate is zero. So you basically have no change in speed. Now, effectively what I just did there is that I connected both velocity to acceleration. Now, I'll try to explain it from the forces perspective. And instead of a person, let's say a ball. You have a ball, it's just about to fall. Like literally at the moment where you move slider away is going to fall. So I'm going to draw the F body diagram. So at this moment, the only force that's acting on the ball is gravity. And so acceleration is effectively g. Now it's falling, it's falling, it's falling. Now at this point, there's gravity, so same amount, but there's also another force which is acting in this direction, and it's going to be a little, not too much, but it's the drag force or air resistance. I'm going to call it Fa. So A is going to be a bit less than G, because what's happening is that so F equals ma, your net force is essentially I'm going to put up as positive and down as negative. And so as a result, this A is no longer G. It has to be a bit less. And so it's falling down until it maintains the speed. And so when you're maintaining the speed, so in other words, you're having no change in speed, your acceleration is zero. Hence, from a forces perspective, your air resistance force is equivalent to your gravitational force. So A is equal to G, so F is equal to ma. Not A is equal to G. A is equal to 0. And as a result, you have no net force, hence why your velocity is not changing. So you enter the state and you effectively just maintain the speed you had until you fall to the ground. And if we draw the diagrams, which is arguably one of the more important concepts, your velocity is going to look something like this. So if we draw tangents, probably the most important skill in physics, I'm going to use a different color. This, so it's quite steep, meaning the change in velocity is quite hefty. But notice how that tangent is getting flatter and flatter and flatter. So that's meaning that the rate of change in the velocity is decreasing. So your velocity is still going up, but the rate at which it's increasing is slowing down until the point where you maintain that velocity. Now, if you've studied derivatives, you don't have to, but it's actually a very easy concept because the derivative of a velocity time graph is the acceleration time graph. And so what's happening is that your acceleration starts at pretty much something like g, but then as the ball is going down, that A value is going down, 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 down until it hits 0. And that's representative of the tangents. Because look, this is effectively the representation of all the slope values. The slope values are essentially getting lower and lower and lower. They're still positive, keep in mind, but they're not as high, as positive as they were. So it's going down, 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 down until it approaches 0. And these two graphs are effectively representing what's going on in terminal velocity, but from the force's perspective. Hopefully that made sense. And now we're going to apply some problems in physics paper 1 problems. Keep in mind, you can't have a calculator. So yeah, good luck. The first question is asking that a raindrop falling from rest at time t is equal to 0 reaches terminal velocity. Which graph best represents how the speed v varies with time t? So I'll quickly draw a schematic. You have a raindrop. Apologies. And it's dropped from rest. Yes? Yeah, rest. So your v starts off with 0. So when you're dropping it off, it's going to go fast, 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 fast until, so it's going to have the fastest rate of change in velocity at the moment you leave it. So it starts falling. But then it's the velocity still increasing, but as time progresses, it's not increasing as fast as once it was. And then it approaches a speed called terminal velocity. And so in the graph, this is basically control C, control V from what I just explained to you. The rate of change in velocity is very steep here, but as time progresses, the air resistance force is effectively causing it to somewhat plateau in its velocity. It's not decreasing in velocity, but its rate of change in velocity is decreasing. Very key distinction. And so it plateaus. Sorry, the change is decreasing, rate of change decreasing until it plateaus. And at this point, a is equal to 0. So that's how our graph will look like. And looking at the graph, well, if you look at A, this is indicating a linear relation. Now, that's not possible because this is indicating that there's no rate of change in velocity. But as I've mentioned to you, due to the effect of air resistance, there will be a rate of change in velocity. Hence, this is wrong. D is effectively saying the opposite in the sense that there's 0 rate of change, so it maintains that velocity, but then shoots up, which is not the case. It might be the case if there was once terminal velocity, if there was once air resistance present and then it just vanished. That's possible, but that's not the case here. So that's wrong as well. And then for C, well, so the velocity is increasing, and then something happens here, and then it plateaus, which is not representative of what's happening in terminal velocity. Hence, the answer is B. And the graph, it looks exactly the same. So hopefully this concept made clear to you. I know I didn't draw too much, but it was more of a verbal explanation. Hope that made sense. Let's move on to another problem, which is terminal velocity, but from the acceleration perspective. So you have an object that's dropped from rest. So I'm going to say v is equal to, don't use v, use u, is equal to 0. So it's dropped from rest above the Earth's surface. Air resistance acts on the object, and it's asking that what is the variation of acceleration a with time t from the object. So the best way to think about this, first draw the vt graph. So this is the effective terminal velocity. It's dropped from rest. So as soon as you drop it, you'll have a very steep rate of change in velocity, but once air resistance begins to act more increasingly on the object, it's starting to plateau. And then it approaches terminal velocity. So terminal velocity. And the question is asking the perspective from the acceleration in time. We can correlate this exactly to an AT graph where we simply just draw tangents. Tangent, 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 tangent. So you're noticing how the tangents are basically becoming less positive. So if we draw the tangent, if you draw the AT graph, it's going to pretty much look like that. So, sorry about that. So, again, the rate of change is decreasing, and this is representative of what's happening in the A to T graph. So if we look at A, this is stating that acceleration is constant, which would have been true if there was no resistance, so that's not true. This is stating that acceleration is increasing. So maybe if an object was accelerating, this would make sense. However, what's happening is that the particle is actually is losing acceleration. So it's losing acceleration, so this is not the case as well. A could work. However, based on the graph we drew, it's matching what we've done. Hence, D is the answer. I want to mention a quick disclaimer. Ideally, when you're approaching fluid mechanics or something like drag force, terminal velocity, the graph should kind of instantly pop up to you what you're expecting. Hence why it's pretty important to keep the VT and AT graph in the terminal velocity context pretty much in your head, so understand it first, but then have the muscle memory so that you know what the graph will pretty much look like based on what the question is saying. And it's pretty important, I think, with the concept where it deviates terminal velocity, where it becomes a bit more challenging, is paper 2, but it's quite relatively rare that they'll ask you to draw these graphs, hence why these mostly appear in paper 1. Hopefully the concept is making sense so far. So now the question is basically a comparison or a comparative, somewhat of a comprehension of if you're understanding what's happening with speed and acceleration. So the question is asking, an object is released above the surface of the Earth. Which of the following correctly describes the speed and acceleration before it reaches terminal velocity? So this is interesting. Before it reaches terminal velocity, the object is still increasing in velocity. It's not increasing by as much as it once was in the early stages, but it's definitely still increasing, and it does not remain constant because that's when it hits terminal velocity. That's when the velocity remains constant. The instructions clearly state before. Hence, automatically, this cuts out C and D. Typical physics IB question where you cut out 2 options but you're left with 2 other options. So, now it's asking about acceleration. Remains constant or decreases. So if we go back to the concept of what's happening to the acceleration, once you drop, the moment where you leave it off, acceleration is purely gravitational based. But as it's going down and down and down, air resistance begins to come into effect, meaning that the net acceleration is not just gravity, whereas it's the difference between gravity and the the net force, not net acceleration. The net force is not just solely gravity, rather it's between the air resistance and the gravitational force, meaning because mass stays constant at all times, the acceleration is going to keep going down until it reaches terminal velocity, where the air resistance force is equivalent to the Fg force, meaning that acceleration is 0. Hence, before it reaches terminal velocity, it's certainly decreasing acceleration. Hence, the answer is B. Let's move on to slightly different types of problems. Let's try this one. So very similar concept. So an object is dropped from rest. Air resistance is not negligible. IB will typically tell you, negligible vs non-negligible. Keep that in mind. So if it's negligible, that means you won't have to consider terminal velocity or any type of drag force. Now the question is asking, what is the acceleration of the object at the start of the motion? Start implies that you've pretty much released the ball and it's beginning to fall. Now, the acceleration, let's look at it each time. The acceleration will never increase because the moment you drop it, air resistance does come into play, meaning that the net force will not just be gravity, meaning that, as I've reiterated, it will be between the gravitational and the acceleration force. So, I'll reiterate this one more time. Because the net force is no longer just Fg, it will be between Fg minus Fa. I flipped it this time. Last time I did Fa minus Fg. The net force will go down, meaning if the mass stays constant, the acceleration also has to be going down. So the acceleration cannot be increasing. No way. Constant. The acceleration would be constant if air resistance was negligible, meaning that only gravity is the sole purpose of why the object is actually accelerating or heading downwards. Meaning that the acceleration will be decreasing as soon as you release the ball, because once you release the ball, the net force will be between gravity and the air resistance force. Keep that into mind. So before you release the ball, solely gravity. Moment you release the ball, air resistance is beginning to kick in, meaning the net force will be between gravity and the air resistance force, until at one point where the gravitational force is equivalent to the air resistance force, meaning that the acceleration is now zero because your net force is zero. So juggling concepts between acceleration and velocity, essentially what we're doing is that we're considering different perspectives. They all mean the same thing, but they're just handled differently. I'd say the toughest one in my opinion is velocity, because students will be typically thinking that the velocity is decreasing. It's not that the velocity is decreasing, it's that it's the rate of change in velocity that's decreasing, and that's representative in the acceleration time graph where the acceleration is going down. Now let's try one more. Let's try a bit of a different one. So this is drag force. Okay, let me just spill the beans. Air resistance is the typical scenario where you're in air and the drag force is basically acting upon you. The drag force, when you see this, is typically referring to when an object falls in a fluid. Now, air is a type of fluid, but drag force is more so like relevant to, I think, in the fluid sense, where it's like something like water, something like an oil or a liquid. Hence, they don't directly say air resistance, rather they just generalize it as drag force. Keep in mind, drag force, air resistance is a type of drag force, but drag force is a generic term of what's going on. It's what's preventing the object to continue moving forward. And that's essentially what's happening in the context of terminal velocity. And typically drag force is more applicable to liquids, but another way to think about it is that drag force is the generic term for these resistive forces that act on object when it's moving through a fluid. So the question is asking, an object of weight W is falling vertically at constant speed. That probably should tell you that it's already hit terminal velocity. And then the question is asking, what is the magnitude of the drag force acting on the object? So we've literally gone over this. I know that I didn't want to sound condescending, but we've just gone over this. So if you have the object falling down at constant velocity, so that means that Fg minus Fa is equal to 0 because it's falling at a constant speed. Meaning no change, so delta v is equal to 0, hence the acceleration is also 0. And so Fg minus Fa is equal to 0. So the gravitational force is equivalent to the drag force. Apologies, I should write drag. And so that means that if the weight, so the gravitational force on an object weight is W, that means the magnitude of the drag force is also W. Hence, it's W. These should kind of be falling quickly too, because object weight, constant speed, terminal velocity, and then magnitude drag force equivalent to this because the acceleration is 0, hence C. Now, we've reached the end of the video. Hopefully, the concept of terminal velocity and the drag force is is making sense to you, and relevant to your understanding of velocity and acceleration, because ultimately it's an application of your understanding of velocity and acceleration. So fundamentally you should just understand this VT graph and the AT graph, as well as understanding what's happening as the ball or any object is moving down or within the air. and that's and the fact that there are changes in acceleration, particularly toward the negative side because the acceleration is decreasing. The velocity is still increasing, but its rate of change is decreasing. So I'm going to show you the two questions. I'm going to recommend, actually I'll show you the easy one first. So a parachute is a total mass 70 kgs falling vertically through the air at a constant speed of 8 meters per second. What is the total upward force acting on the parachutist? I think this is not too hard in my opinion. Trust me. If I can get it, you can get it as well. This one, I'd suggest research before trying to do. I think take a guess. Your intuition will confuse you, and your experience will confuse you. Pretty sure. But research after you've done the question. Research after doing question. Parachute terminal velocity. It's actually a very interesting read and one that I found. Actually, I think this is probably the peak in terms of difficulty of terminal velocity because this is the application of the parachute. So, you can read the question, see what's happening, and hopefully get the answer. Hopefully this has been a comprehensive guide towards terminal velocity and the understanding of drag forces. I think this is more or less what the IB will ask you on paper 1. Paper 2, they'll probably ask you to draw the graphs in a particular case, which I don't think is too bad. All you just need to understand is the VT graph. So hopefully you enjoyed the video. Please like and subscribe to IB45 or Gone.